It really was though, right?
It was.
They're like, okay. Hey there. We're gonna talk about some math, okay? My grandmother talked like that, so it's okay. Okay, so we got kind of a short one today because it's just going over the subtraction and multiplication. Last class we introduced sort of the concept of other bases, and for computing, there's only really two that you kind of care about. Well, three technically, but one of them you already know, and that's base 10. You already know base 10. So we care about binary and hexadecimal, base 2 and base 16. And especially base 2, because there are circumstances where you would want to use bitwise operators in your programming language, especially if you're working in C or C++ or Rust, something more low level. You will be using bitwise operators, and they operate on the bits directly. So understanding what a variable of 10 in binary is can be very useful. So that's why we talked about it. And hexadecimal is used in lots of places in computing too. So just kind of understanding it is good to have. And then for the purposes of just exploring abstraction and algorithms, we started talking about addition in these other bases and sort of exploring that it doesn't really matter what base we're working in, right? The process is still the same. It's just sort of our exchange rate that matters. I have a question mark here because I did at least one example, and I don't remember if I did the two that I wanted. So I'm going to do another one just to be safe. So we're going to start off with addition, just to make sure, cover our bases. So we're going to do this the same way I always like doing it. Give me a base.
13.
All right. Now give me a base 13 number.
93.
Sure, yeah, I'll put that down here. And then I'll invent one too. You know what? I always make you do all the work. So I'll do one too. So base 13 has the weird digits in it. So
ABC.
I could do ABC. I'm going to save that one for later.
Okay.
I'm going to store that in the memory banks. So the point with base 13 addition is it's the same as base 10. It's just we have to care about the exchange rate. So you know what? We're going back to ABCs. I just started looking at this and I was like, this isn't going to work. So we're going to do ABC plus 9,3 in base 13. So remember, this represents 10, this represents 11, and this represents 12. So it is a single digit representation of that number. So we do C plus 3 on the side here. This is numerically 12 plus 3, right? Because we're trying to draw the distinction here between these are the symbols that represent these numbers. But over here, now we're actually working with the numbers. So we don't have to worry about the symbols anymore, right? We can just write down the numbers because we work in base 10. So we can just write down the numbers. So 12 plus 13, or 12 plus 3 is 15. So what we do is we say, I have an exchange rate here. What's the exchange rate? 13. Every time I get to 13, I exchange that, I carry it to the left, and write down whatever's left over. So in this case, we've got our 1, 13 that we have to carry over. What do we got left? We got a 2 left over. So we're going to go ahead and we're going to write down that 2. We're going to carry this 1 and then repeat, right? Same as regular addition. So now we do B plus 9 plus the 1 we carried. Like this. I'm going to move that down. So 10 plus 11, 21. So that's 1, 13, and then 8 left over. So we write down the leftover. Carry the 1. So this is A plus 1. So number-wise, this is 11. So when we have 11, that's the symbol B. And we're done, right? Addition is a relatively simple algorithm to implement. ABC in base 13 added together with 9,3 is B8,2. And so this is kind of, so this topic, like base conversions and stuff like that, is a pretty standard, I would say, discrete math topic, like what we're talking about. But the interesting thing is you guys are in programming, so you get to have the fun part of all of this stuff, because when you're showing this to discrete math classes, you would show them these algorithms, and then they would, it's the calculus question of, hey, cool, Travis, you showed me this algorithm. Well, when am I going to use it? And in that class, I'd be like, oh, on the homework. And they'd be like, okay, but what about other than that? And then I would be like, well, the homework. But here, well, for one, the abstraction is the importance here for programming, right? You are abstracting concepts. Again, I've sort of mentioned how that's an important skill to develop, but you get to have the fun of, hey, the reason why we're covering this and explaining how the only thing that matters here is the exchange rate is that makes it pretty easy to implement as an algorithm in a computer that only cares about the exchange rate. So, spoilers, I want you to do that on assignments because you can program. So you will this is why the algorithm is important rather than just the answer, because technically you could just ask Wolfram Alpha for these things, right? And that's kind of always the thing with math, right? Is the understanding of the algorithms and the underlying concepts that we care about, not the answer. I know my computer can give me this answer. I don't need you to give me this answer, but understanding the algorithm lets you implement it and tweak it and all that sort of stuff, right? So that's why it's interesting. So okay, that covers addition. So now we're going to talk about subtraction in other bases. And fortunately, subtraction is basically the same as addition. It's all all these are the same. The only thing we care about is the exchange rate, right? That's what we're really concerned with. So for subtraction, it's not too terribly different from addition, other than the fact that we're doing subtraction instead of addition. So we're just going to jump straight in with an example in base 5. So this is what we've got. So the way this works, if we were working in, say, base 10, is we want to do 2 minus 4, right? Which we can't do. And now, of course, you could say, well, what about negative numbers? The point that's not the point in this algorithm, right? This algorithm does not include negative numbers until you get to the very last one here on the left. If we did, 1 minus 4, then we would have a negative number, right? That's when we care about it. Until then, we don't. So we would say, can't do this. So in this standard algorithm for subtraction, what we do is we borrow. So what does this look like? Well, in the standard algorithm, what you're used to is we would cross this out, write a 0, and then if we were working in base 10, what we would say is this is 12, right? That's the standard algorithm. We're not working in base 10, though. We're working in base 5. But the idea is still the same. The difference is the exchange rate, right? Instead of taking 10, we're taking 5. So we cross out the 2 and we add 7. So we can kind of see what's happening here if we think in terms of our place value charts. So there's stuff over here, right? There's the rest of the digits. But let's just worry about these. So we've got our 1 pip here and 2 here. And we've got 2 here. And we're trying to take away 4. Right, so the point is we can't. What we need to do is we need to exchange. Right, so we're going to take this and go in reverse. Right, so when we're doing addition and base conversions, we're used to taking 5 of these and adding 1 here. We could do the opposite, right? We could take 1 here and add 5 over here. Right, these are the same things. Right, so we have taken 1 of these away and added 5 over. Right, that's one of the important properties of these bases. Right. Take 5 from here, add 1 here. Take 1 away from here, add 5 here. And so now we've got 7 pips minus 4, that's 3, right? So 7 minus 4, we write down 3. And this is sort of the underlying idea of what's happening with borrowing. But now we just rinse and repeat, right? 0 minus 2, we can't, so we have to borrow. So we cross that out, and we just borrowed 5. 5 minus 2, we get 3. 3 minus 1 is 2, right? So 4, 1, 2 in base 5 minus 1, 2, 4, 2, 3, 3. And so again, this algorithm doesn't care that we're working in base 5 other than the amount we have to borrow, right? And also, of course, the maximum digits that we can use, right? We can't write down 6 as a digit because that's not valid in our base. But those are the only two situations where we really care. The algorithm remains unchanged. So let's just do another example with a bit more complicated borrowing. So we're going to do base 11. So we're doing A01 minus 1A8. So this is the subtraction we're doing now. Again, remember, we're in base 11, so A represents 10 as a digit. So right off the bat, we need to do 1 minus 8, so we have to borrow, right? But now we look and we say, okay, I need to borrow 1 from here. I can't, though, because that's 0. So I have to borrow from here to make this not 0. So this is going to be dropped down to 9. I cross this out, and now this gets into some kind of technical nitty-gritty that I don't actually care about, so I'm just going to give you some options here. So the question is, what do we write? So the natural thing is we just cross this out. We're borrowing 11, so we write 11. Now, in a technical sense, this is a problem because that is 2 digits, and we probably shouldn't be doing that. So technically, don't worry about this, but this would actually be 1, 0 in base 11. That's obviously, that requires you to think way too much, so we don't want to do that. So a couple things you can do. We kind of did it here. I wrote down a 5. Technically, 5 isn't a valid digit in base 5 either, right? So you can just write down 11, and I understand what you mean, right? At this point, this thing right here is not base 11. It's just the number 11, right? Another thing you can do that I like to do to just really drive it home is I write the word 11, some other representation of that, so that we know we're talking about the number 11, right? Not some representation of it. Another thing you can do, and I think a lot of students prefer doing this, is, well, technically B is not a valid digit in base 11, but we know that it's valid in base 16, right? We know we could go A, B, C, D, E, F for all of the digits. So you could just use those two, right? So we borrowed 11. The digit for 10 is A, so the digit for 11 is B, right? All of these are fine. I'm okay with all of them, so that's why I'm just sort of presenting them. So you don't have to worry about, what do I write here? Whatever you want, basically. Just indicate that this is 11, right? We borrowed 11 from here, so we're writing 11. But now, why did we do this? Well, because we wanted to borrow from here, right? We have to remember that's the whole reason we did this. We're trying to do 1 minus 8, so we needed to borrow. We couldn't, so we borrowed from here. Now we can borrow from here. Cross this out, and we write A. Cross this out, and again, this is going to be 11 plus 1, so that's 12. So you can write C, you can write 12. All of these are fine. You could write the number 12 in base 10. All of these are fine. I'm not going to be picky about it. But now we're in a good situation. 12 minus 8, we can do that. That's 4. A minus A, so that's 10 minus 10, that's 0. 9 minus 1 is 8. And so then that means A01 minus, in base 11, 1A8 is 804. So with subtraction, the main thing we have to be paying attention to is when we carry, our exchange rate is different again, right? So if we were working in base 10, when we borrowed, we would just write 10, right? In this case. But now the base is what we write. That's what changes. And of course, the digits that we can write is what changes. So, okay, subtraction is pretty similar to addition. So there's 2 other operations we, oh yeah.
How did we get the 12?
Where? Oh, here? Because we borrowed 1 from here, so we add 11 to 1 and get 12. Right? Because that's, if we were working in base 10, that's how the algorithm would work, right? We would want to borrow from here, can't, so we borrow from here, get this to be 11, take 1 away to add to this. So we have multiplication to talk about, and technically, we could do division. Now, we're not going to, for one reason. If I want you to do it, it would be explained in the group project, because the thing, we don't want to get lost in the forest, and doing the division algorithm in another base requires you to do really, really good subtraction in that base, because division, so multiplication is repeated addition, division is repeated subtraction, right? You've got your 263 divided by 5 is basically the answer to the question, how many times does 5 fit into that, right? So I just repeatedly subtract 5 to find out how many times I can take it away. That's what division is. So if we want to do it in another base, we're just doing that, but in base 7. So now you have to do base 7 subtraction in your head a bunch of times, and that's not very reasonable. that's well, like, you could do it, but if I made you do it and if I presented it in front of the class, you'd be like, Travis sucks. And then you would be doing by hand on the assignment, you'd be like, I think I screwed it up, right? It's just, it's going to be hard. Computers, though, can do that really well, because then you don't have to yourself keep track of the base. Your variable tree keeps track of the base, right? So your computer can do that algorithm pretty nicely. So that, we'll leave that for basically programming. But multiplication, though, is something we can very easily do by hand, because it ultimately just is a bunch of addition. And addition doesn't have to worry about that, like, borrowing and stuff like that. Yeah.
What if there is a 2 at the place of 1?
Where? Here?
Yeah.
Then it would be 13.
Right?
Yeah. You just take the base and add it to whatever that number is. Yeah. Okay, so let's, for multiplication, let's go back to starting with an example of something that we know. Again, most of these algorithms, if you're my age at least, you've seen them before, but if you're my age, it was almost 30 years ago. So can't fault you for not remembering it. And even if you're 18, it's been probably 10 years since you've seen these. So I don't expect you to remember them. So that's why we're covering them again. So let's talk about base 10 multiplication. I'm going to bust out my different colors here because it helps me keep track of things. So, okay, the way this algorithm works is we say 4 times 7, that's 28. So we write an 8 and carry a 2. 4 times 3 is 12, plus 2 is 14. Carry a 1. 4 times 0 plus 1 is 1, right? This is how that algorithm works. Essentially, what we just answered is the question 37 times 4, right? Which, if you knew times tables like really big, you could just do that in your head. The reason why we use this algorithm historically is because it boils multiplication down to, you need to know your times tables for 1 to 9, right? Because you'll never deal with digits bigger than that. So you need to know multiplication tables for 1 to 9. Okay, but then what do we do next? Well, we write a 0 down here and sort of just repeat, right? We cross out our carries. We don't need those anymore. Those are for the previous step. And we do the same thing, but with this digit now. 2 times 7. So 2 times 7 is 14. Carry the 1. 2 times 6, or 2 times 3 is 6, plus 1 is 7. And we're done. So what we just did there was we answered the question. So the reason why we write the 0 here is because this is 2, 0, right? So we just answered the question 37 times 20, right? So if you go to your calculator and say, what's 37 times 20, it's 740. Alternatively, 2 times 37 is 74, times 10 gives you 740, right? So that's why we do this algorithm this way. And now the question is 37 times 4 plus 20 times 37. Add those up, we get 24 times 37, right? This is just properties of multiplication, ultimately. So 8 plus 0 is 8. 4 plus 4 is 8. 1 plus 7 is 8. Okay, well, all right. 8, 8, 8. But the point here is, so this is just the algorithm. I'm presenting it kind of fast because we're going to do a bunch of examples at other bases, so we're going to spend time on it. But this is the algorithm that you would have been taught in grade school, right? This is the method. Well, let's try to break it down here and think about what's happening, because our goal is to sort of abstract this technique into other bases, right? Take it from base 10 and make it so that we can work in base 6 or base 14 or whatever, right? So what's really going on here? Well, let's take a look at our very, very first step. We did 4 times 7. So that was 28, right? We're going to have to know these times tables, essentially, right? So to be clear, for these, I know my times tables. If you don't, I'm not going to judge you. Use your calculator for these parts, right? If you can't remember what 7 times 8 is, then plug it into your calculator. So here, we look and we say, okay, I need to carry, right? But how much do I carry? Well, this is 2 copies of 10 with 8 left over. So I write down the 8 because this is essentially the ones digit here, and I am carrying 2 copies of the 10 to the tens digit, right? That's really what's happening here. So I'm writing down the 8, and then I carry a 2 because I want to add 20 to the tens digit, right? So now I do 4 times 3, which is 12, but then I add the 20 or the 2 that I just had to get 14. Really in the background, this is 140, but we're not really worrying too much about that. It doesn't really matter for the algorithm, but that's what's happening. But again, same thing. There's one group of 10 with 4 left over. So we write down the 4, carry a 1, and then we do 4 times 0 plus 1, and we get that 1, right? So that's what's happening with this algorithm. So let's take a note here. The only place where we're actually carrying about 10, right there, right? And also which digits that we can write down, right? But if we're paying attention to that here, we'll never have to worry about that, right? This is the only part that matters. So again, it's an exchange rate situation, right? It's just now, instead of usually exchanging 1, we can exchange more than 1, 2 in this case. So let's see if we can adapt this strategy to other bases. We're going to do a base 4 one, and the nice thing about multiplication in other bases, and actually it is very fortuitous, that the smaller the base we get, the easier the multiplication becomes, because you have to carry less things, right? If we only have 4 digits possible, then this can be either 1, 2, or 3. It's never going to be 4 or bigger, right? That means when we're in binary, this carry digit is either a 0 or a 1, which actually ends up being very convenient for computers doing multiplication. That's why they're really good at it, is because there's sort of bit shifts that you can do to do this multiplication very easily. But let's just explore the algorithm for base 4 to kind of see what I mean, right? This is going to be, if it were the first time you were ever presented multiplication, base 4 multiplication would actually be easier than base 10 because you need to know less times tables. So we're going to do, the bottom number is 12, or 1, 2, and then I've got 1, 3, 2. So this is the multiplication we're doing. So what do? Same exact thing here. All right, we start at this number and we say, what's this number times this number? So what's 2 times 1? That's 2. Well, that's not bigger than 4, so we don't have to do anything, right? We just write down 2. If you want to think about it this way, this is 0 copies of 4 plus 2. We write down the 2. and we don't carry anything, right? I don't think this is a super useful way of thinking about it. But if you were writing an algorithm in a computer, you would probably keep track of that. It's probably the easier way to do it if you're doing it iteratively. All right, next step. We've got 2 times 3. That's 6. Okay, perfect. That's bigger than 4, which is our base, right? So that means we're going to figure out how many times does 4 fit in here once with 2 left over, right? So we take this leftover, and that's what we're going to write. Right, so we're writing this sort of leftover piece down, and we have to carry a 1. Carry that 1 to the next step. Now this is 2 times 2 plus 1. In terms of numbers, again, this is what I'm doing here. So you might be thinking we're working in base 4, but over here you're working in base 10. What's happening is this is the symbols that represent these numbers. Over here, I'm just saying, no, we're just dealing with the numbers. We're disregarding the symbols now. It just so happens that we universally work in base 10, well, almost universally. So the symbols and the numbers are the same in base 10. So we can write in base 10. But this is 5. So same exact thing. We've got 1 copy of 4 with 1 left over. So we're going to carry a 1, but we're going to write down this one. We carried a 1. So we got 1, 1, 2, 2. And now we repeat. So we write down a 0 here, same as we do over here for base 10, and we do the same thing. Now, fortunately, this one's pretty straightforward because it's 1 times a bunch of stuff. So 1 times 1 is 1. We write down a 1. 1 times 3 is 3. So, okay, we write down a 3. And 1 times 2 is 2. So we write down a 2. All right, that was nice. Okay, now, just like over here, we need to add it up. But this is, if there's one mistake that students make, it's right here. This is base 4. We are always working in base 4 here. Like, again, this is, we're dealing with the numbers, not the representations of them. Here, though, this stuff is base 4. Anything you do on the side doesn't have to be. So the most common mistake that students make is everything here is totally correct. They have all of this. This is super correct. And then they add it in base 10, right? Just because instinct kicks in at this point, right? You would just go 1 plus 3 is 4, and you write down 4. And it's like, no, we're in base 4, so we have to still pay attention to that. So 2 plus 0, okay, that's 2. 2 plus 1, that's 3. 1 plus 3, there we go. That is 4 or bigger, so we do have to make an exchange now. So we're going to write down that 0 and carry this 1. 1 plus 1 plus 2 is again 4. So same exact thing. We write down the leftover, which is 0. Carry a 1. These are all 0, so it's 1. And we're done. So 2, 3, 1 in base 4 multiplied with 1, 2 is 1, 0, 0, 3, 2. And now this is kind of what I meant when I said it's quote unquote easier in base 4, because these carries will always be smaller, right? They can only be at most 3, right? So that saves us a lot of effort, right? Over here, we could have a 9, technically. Well, actually, I think we can't, but because 81 is the biggest. So we would have an 8 that we have to carry, right, in base 10. But over here, maximum 4. Okay, so let's actually try this again, but in a different base. So we're going to do base 11. So let's do I need all my colors, probably. So we're gonna do 1A, and now class participation. Give me a number in base 11. 3 digits. 264. Okay, perfect. Doesn't matter to me what it is. And that's kind of the reason why I do that is to, again, show that like it doesn't matter what we do. The algorithm is going to be the same either way. So let's go through the motions here. So 4 times 1. Now, if you look over here, I was kind of writing down unnecessary steps, right? Right here, 2 times 1, there's nothing to carry. We don't really have anything to keep track of. So we could technically just do this in our head. I mean, any of this could be done in our head technically, but there's nothing to do, right? We just write down the answer. So you can do that too, right? Right here, 4 times 1, well, that's 4, right? There's no work to be done. But if you're more comfortable writing it all down, by all means, go ahead. Here, though, we have A times 4. Now, I'm writing it this way, again, because we're trying to unpack what the symbols mean in terms of what they are as numbers. So A is 10 times 4, so this is 40. Right, we're sort of translating the symbols from here into what they are as numbers. Now we're working with just the numbers. This is 40. So we have to do an exchange here, right? This is bigger than 11. So now we have to ask ourselves, essentially, how many times does 11 fit in here, right? How many do we have to carry over? So we think 11, 22, 33, can't go any bigger than that, right? If we did, we would be at 44, that's bigger than 40, so we're not going to carry any more than that. So 33 is 3 times 11. And now we say, okay, well, that's 33. What's left over? That's what we write down, right? Whatever's left over. 7. So we're going to write down the leftover, which is 7. And we're going to carry our 3. And again, there's always this sort of 0 kicking around there. 4 times 0 plus 3 is 3. And now we rinse and repeat. So we get rid of our carries because we're done with that step. We write down our 0. And we chug along. So again, 6 times 1. There's nothing to be done, right? We just write 6. Perfect. Now we've got 6 times A. So we unpack that. A is 10 times 6, so we've got 60. Same thing. We ask ourselves, how many times do we have to essentially exchange 11? So 5. Yeah. 5 times 11 is 55 with 5 left over. We go ahead and we write down that leftover piece, and we carry the number in front of the 11. 6 times 0 is 0, plus the 5, we write down the 5. And again, we repeat. So now when we just keep adding zeros, the more digits we have here, right? So now we add another 0. 2 times 1 is 2, so we don't have to do anything. 2 times A, or I've been writing it as A times 2. So what do we got? That's 20. Well, 11 only goes in once. And we got 9 left over, so we write down the leftover. We carry that 1 right there. 2 times 0 plus 1 is 1, and we're good. Now we have to do this big addition, and again, it is in base 11. You have to pay attention to that. You have to make sure we do it in base 11. 4 plus 0 is 4. 7 plus 6 is 13. Well, 7 plus 6 is 13. And again, this is where people tend to make the mistake, honestly, in these questions, is either they'll write 13, which, no, that's 2 digits, right? So not that. Or they'll do it in like if it's bigger than base 10, they'll write that. They'll write 13. If it's lower than base 10, then they'll just write like 9 when we're in base 6. So just pay attention to that. So we're not going to make that mistake. We've got 13. So that is 11 fits in once with 2 left over. We write down the leftover and carry the 1. So 1 plus 3 plus 5 plus 2 is, 11. Ah, okay. It's 1 copy of 11 with nothing left over. So we write down the 0 and we carry that 1. 1 plus 5 plus 9, I'm running out of space, is 15. So that's 1 copy of 11 plus 4. Write down that leftover, carry the 1. 1 plus 1 is 2. And we're done. Right? So again, these, it didn't matter. The only thing that was different was this exchange rate, right? And it's a little hard conceptually to wrap your head around it at first, but that's the only difference, right? Honestly, the thing that most people struggle with in this is just remembering how to do long addition and multiplication. Because again, it's been at a minimum probably like 8 or 9 years. If you're 18 fresh out of high school, which who here is fresh out of high school? I have my hand up as if I'm fresh out of high school. I'm not. I'm 36. So yeah, nobody here is fresh out of high school. So again, probably at least 10 years, probably way more than that. Like again, for me, it's we're getting closer to it being 30 years for me since I was taught this algorithm. Let's say 27 years. So yeah, that's the part that people are usually like unsure about. Cause like, you just need to do it to remember it, right? But I'm going to leave these on the board so that you can refer to them for the quiz, which, hooray, quiz. Yep. Sorry, what? Which one? Subtraction. So which part of it are you stuck on?
Like last one you explained.
So, I mean, I can just do a quick example. Would that help? Okay. So let's do, because I think I know what you're probably stuck on. Like this, right? So we want to take away 3 from 1, but we can't. We need to borrow, right? So we need to borrow from here, but we can't because this is 0. So we need to make this not 0. So we have to come over here and we're going to take away one of these. So we take that to 2. Cross this out. We've borrowed 5. That's our base, right? So we're borrowing 5. So this becomes 5, right? Now our goal was to borrow for this. So now we're going to borrow. We're looking at this and we're going, okay, I need to do 1 minus 3. I can't. I need to borrow. I look over here. This is 5 now. So I can borrow from that. Cross that out. It becomes 4. Now I've just borrowed 5. So cross that out. It becomes 6, right? I'm borrowing 5. I'm adding the 5 to that 6. Now things are looking nice. I can go, okay, 6 minus 3, that's 3. 4 minus 2 is 2. 2 minus 0 is 2, right? So it's just keeping track of that borrowing. And I mean, you could actually even, well, no, you can't. I was going to say you could make it more complicated, but this is kind of the situation that I wanted to cover where you have to sort of borrow more than once. If you've got zeros, you'll have to borrow more. You'll have to like keep moving left until you can actually borrow, right? Does that make sense?
And what if we get 3001 minus 23? Oh, yeah.
So like this.
Yeah.
Same thing. So I want to borrow from here. I can't. So I have to come here to borrow. I can't. So I come from here and I borrow from there. Cross that out, put the 5 there. And go back to this. I'm like, okay, I need to borrow. Can't. I need to borrow. So I borrow from here. And then now I can borrow to here. So 6 minus 3 is 3. 4 minus 2 is 2. 4 minus 0 is 4. 2 minus 0 is 2. All right, so you just repeatedly borrow from the left until you can. Yeah. And you can get situations where you have 2, 0, 1, 0, 0, 3, right? So you take away from this, and now you've created a 0 there. So now you have to, when you come there, you have to borrow more, right? So it's just keeping track of those borrowings.
I'm just curious about the variables for assigned lettering. Is that like a set variable number, or is it pertaining to the question itself?
Do you mean like the A, B, C, that sort of?
Yeah.
So we choose, so I choose A, B, C because that matches hexadecimal. So is it preset? Yes, in the sense of if you're looking at your computer, hexadecimal's already been decided like 60 years ago or whatever. And those are the symbols they chose. But in terms of, does it actually have to be that? No, it could be whatever symbol you want. We just chose a convenient one. But I will always write A, B, C. So
okay, I just didn't know if it was going to change from like uppercase A would be.
No.
Like
I'll always match hexadecimal. And I encourage you to as well, just so that you're consistent with like, you know, CSS and HTML uses hexadecimal, and technically it doesn't care if you use uppercase or lowercase in CSS, but it's still the letter A, uppercase or lowercase, means 10, right? So I just always write caps so that it's like there's no ambiguity, because some letters can look like numbers. Like let's hope we never get there, but is that an O or a 0? So if you're getting that far, you're probably gonna be like, I need different symbols, right? I'm not gonna use O. But like A, B, C, D, E, F look distinct enough from the number symbols. That's why we chose them, probably. We could have just invented new symbols for them, right? Like I could have been like, this squiggly is the symbol for 10. But then that's kind of cumbersome. So that's, again, why we just chose like A, because, well, A is an ASCII character. So it's easy to represent in computers. So that's why we chose it. So yeah, I mean, that's a good question. Like, yeah, it's arbitrary, but we have decided to just use those symbols. I won't change them. If you submitted like you did a base 12 multiplication and you use different symbols, I'd be like, okay, whatever, right? Like that's fine. I've seen, so when I teach this to like discrete math students, non-computing, I might say like in base 12, I might go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, T for 10, E for 11, right? Just so that they don't know hexadecimal, right? They've never seen it before, and they're never going to see it in a discrete math class. But the fact that you guys are in HTML, you have seen hexadecimal, so that's why I'm matching that.
Yeah.
But this is something I have seen before. When you get to base 13, now it kind of doesn't work anymore because it's T10 or 13 or 12, right? Like you have to invent new symbols. But yeah, I mean, I just stick with the hexadecimal stuff. And if you want to write it in lowercase, go ahead. Doesn't matter. I'm okay with that. So with that, I will hand out my gift.